In this recording, we're going to talk about metallicity. Metallicity is the measure of abundances in space, but let's start at the beginning. So what is metallicity? Well, assuming that we accept the Big Bang as our origin of the universe, then very shortly after the Big Bang you have lots of hydrogen, lots of helium, and pretty much nothing else. And you have to make all the other elements inside of stars through nucleosynthesis. So hydrogen, wherever it is primordial. It comes from the beginning of the universe. Helium may have been formed in stars, lots of it is, but actually still most of it is primordial. And then all the other elements that we see, we tend to refer to as metals. We know they're not metals in the chemical sense, but it's just a way of distinguishing between these primordial elements, hydrogen, helium, and other elements. And so metallicity is a measure of how much other heavy elements we have. So I just want to show you a Hertzsprung-Russell diagram. Here we can see we've got hydrogen up here and helium up here, and then all these other elements don't exist at the beginning of the universe. And so what we're talking about is the abundance of all of these. And obviously they may not all have the same relative abundances. So you might have something that's got lots of oxygen but not much nitrogen, or lots of oxygen but not much carbon, and vice versa. So while metallicity is grossly a measure of what we have as the abundance of heavy elements, in reality we tend to measure it in terms of either the abundance of oxygen relative to hydrogen, which is our primordial element, or actually more normally is the abundance of iron. And those two elements form in different places, as do all the other things. So we'll get into the complications of this later, but for now let's just say it's some measure of how much heavy elements there are. So it's the proportion of metals compared to hydrogen. Like I said, it's usually a measure of iron or oxygen. And we get this by looking at the spectrum. We've already talked about how we use the spectrum to determine temperature, but then when you look at it in detail, you can also take out how much of different elements you have relative to hydrogen from the strength of various absorption and or emission lines. So we've got what is the ratio, and then we define this as X over H. So it's usually Fe for iron over H. Sometimes it's O, sometimes we use other things, we'll see in a few minutes. And then we plot it on a logarithmic scale. That's usually what the square brackets denote. And so if we've got a metallicity of Fe over H is -1, it means that the iron abundance is a tenth that found in the sun. And likewise, if it's Fe over H is +1, then it's 10 times the solar value. So that brings us to the idea of different populations of stars, and grossly you can think of this as being two divisions, things that are like the sun and things that are much lower in heavy elements. So population 1 stars have very high levels of heavy elements, whereas population 2 stars have much lower heavy element abundances. Population 1 stars are relatively young. This is an oversimplification, which we'll come back to. But basically you can think of it as being a population 1 star is relatively newly formed because you had lots of heavy elements already available to it. So even if it seems evolved, like it's a red giant or a supergiant, it's still relatively young in the sense that lots of metals were incorporated into it. Likewise, if you've got a population 2 star, it might still be a main sequence star if it's a red dwarf or something, but it's quite old, because it was formed before there were lots of heavy elements. So there's some tweaks to how we want to think about this as we go along. So what population is the sun? Well, I already hinted at this. The population of the sun is 1. It's a young metal-rich star. In fact, its metallicity, if you want to take this in terms of how much of the sun is made up of elements more massive than helium, it's 1.6% by mass, or about 0.1% if you do it by number of atoms, because remember the more massive elements represent more mass, obviously. So how do we know that the sun was formed out of materials that was processed through other stars? Well, we're here. Only 10% of our bodies is made of hydrogen and helium, and the rest of it comes from those heavy elements. The Earth is predominantly oxygen, and then magnesium, iron, and silicon, all of which come from other stars. So it must be at least second generation. You have to have made some heavy elements before the sun was formed. But actually it's at least third generation. We'll talk about how complicated generations are in stars later. But basically what we have is that we have things that we find in the solar system that have compositions that show they formed outside the solar system, usually from the isotopic compositions, and these are usually found in meteorites, and we call them pre-solar. And if it's a pre-solar grain, it means that it survived the formation of the solar system. So we have these grains, but they actually come from stars that are low mass like the Sun, and already have some heavy elements like silicon in them, but those heavy elements weren't formed in those stars. And those have been thrown out of a dying star and then donated to the solar system before it formed. So we have to be at least third generation. Population 2 stars are generally considered to be old, since the ISM, the interstellar medium, the gas from which it formed was metal poor. So we'll come back to that idea shortly. And if this is true, then only the low mass stars still exist, because high mass stars evolve quickly and low mass stars evolve slowly, and so the high mass stars would already have evolved and died. So what about population 3? Population 1 is high metallicity, population 2 is low metallicity, and population 3 would be the oldest stars, the stars that were first formed. And we estimate the metallicities, this is basically the very first stars that were formed have to have less than 1/1,000,000th of the sun's metallicity. There has to be very little over and above the hydrogen helium. And basically these things are still hypothetical. We're still looking, they're very hard to spot, because we have to be looking at things that have been around for a long time, or we have to be looking back in time to very faint things. So let's look at the slight complications in metallicity. So there's a metallicity gradient through the galaxy. In general, the metallicity is higher closer into the galaxy and lower further away. You can see here it's actually even more complicated than that. And this can be understood in terms of the star density. Basically what you've got is that the density of stars means that you have more stars born and die and throw out heavy elements, and so you have more heavy elements available to you quicker in those dense regions. And so if you're in a spiral arm as opposed to in between the arms, then you're going to have more metals right now. And if you're in the center, you've got more stars, and so you've been able to build up higher metallicity. And as you move out, it gets lower. But it's actually a little more complicated than that. So here's like a schematic, and this is actually done from the point of view of magnesium. And again, we'll come back to the issues of metallicity and the different elements that we can use. But you can see here that we have, more stars as we move in, less stars as we move out. But for the old stars, they're actually higher above the plane. So not just in the galactic plane, but also in a halo around it. And so it gets a little more complicated. This is another way of looking at this. So here we have, here's the plane of the galaxy, here's the galactic bulge, the sun's somewhere over here, and if we look at the stars in the plane right here, we get an increase in metallicity as we move towards the inner regions. But if we look up at this zone up here, where we're above the plane, then actually the change in metallicity is not so much, but it's much lower than the metallicity of the sun. So there's a change going in this direction as well as going in this direction. So this is actually based on observations, just to kind of orient you to this little blurry image up here. This is the galaxy, that's the bulge, this is the axis, and this thing that we're looking at is this wedge shape here, just to kind of put it in perspective. And this is 2.5 million F-type stars that we use to make this plot. And here you can see this is in kiloparsecs, so this is distance from the center of the galaxy, and this is the distance above the plane of the galaxy. So here we're in halo, so here we're in the disk, and we've got high metallicity, and as we move up, we head into much, much lower metallicity. So being in the mid-plane makes us much higher metallicity, and even looking in our own galaxy outwards, we have much lower metallicity. So something born up here will have lower metallicity, even if it was born now. And so we have to be a little bit careful about interpreting metallicity and age. But this is kind of an overall distribution. You've got things that are extremely metal rich in the center of the galaxy. As you move out, the metallicity goes down, and then as you move up in height, you get things that are population 1 and 2 mixed up, and then you've got very, very low metallicity population 2 stars up here. So that's what happens in our galaxy, but what else do we have? Where else do we find stars? Well, there are other galaxies. Now, I want to orient you to this. So here we have kind of a schematic of our local neighborhood. Here's the Milky Way and all of these galaxies that kind of orbit us. And here's the sister galaxy Andromeda and these other galaxies that are orbiting around Andromeda. And here you kind of see a 3D structure. So instead, if you were looking down in this direction, this is what we'd see. But you can see that here's the large and small Magellanic Cloud, which are below. So even though they look like they're in the same plane, they're below the Milky Way. And actually, you need to be in the southern hemisphere to see them. This is the large Magellanic Cloud and the small Magellanic Cloud. And these things are actually orbiting the Milky Way. But these have lower metallicity than our own galaxy. So whereas we tend to think of our galaxy as averaging about that of the Sun, even though it ranges from 10 times higher to 10 times lower or so, depending on whether you're in the halo or in the center. But when we want to get to the LMC as a whole has an average metallicity of about half that. Actually, it's about 40% that of the Sun. And the SMC, the Small Magellanic Cloud, has an even lower metallicity. It's about 1/10 that of the Sun. And again, that's on average across the whole galaxy. They're smaller galaxies, so again, this is just another view to give you a kind of 3D perspective on this. So as you move away, this is how far away these things are. But here you can see the large and small Magellanic Cloud. The large Magellanic Cloud is 50 kiloparsecs away. The small is more like 75 kiloparsecs away. They're close enough to be able to resolve individual stars, but they are much smaller than our galaxy, and so the total amount of star formation that's happened, the total amount of metals that have been thrown in there is much lower, and so you can understand why they have this lower metallicity. And so metallicity has an effect on stellar evolution. So it affects what's in the star when it's born, but then it also affects what happens after it's born. And we're going to get into that in some detail as we get into the evolution of stars. But just to kind of put this in perspective, if you've got a population 1 star, it's about 1% other stuff, not hydrogen and helium. Population 2 is about 1/100th of that, 0.01%. And so they've got a lot less metals, and so that's going to affect all sorts of things like energy flow and how these things evolve. And it's the exact amount, and actually the proportions will affect how the stars evolve. So for pre-main sequence and main sequence evolution, it tends to be fairly similar, although we'll talk about that in a second. But the bigger effect happens when you're in the post-main sequence evolution. So let's just talk briefly about these compositional effects. So because we have these differences in composition and they affect the flow of energy, you can imagine that you've got a star that's kind of like the Sun but has more metals. It's going to affect how the energy flows, so it's going to affect the way in which the energy gets out from the center. It's also going to affect how much energy you can make, because it's going to affect the nucleosynthesis in the core. And so you might have something that's not quite the same. It's going to be very slightly different, either slightly hotter or slightly cooler, slightly brighter, slightly less bright, depending on the exact metallicity. So when we look at the main sequence, it should be more of a band than a simple line, because at any given temperature or luminosity, you could have different metallicities. And so there will be this kind of spread around them. And I just want to point out, as it says in this bullet here, something like the Sun, it's basically going to stay really close to this point the whole time. It does evolve slightly, which we will get onto. It does evolve a little during the main sequence, but it's a very subtle effect. It certainly is not going to change hugely and travel up and down the main sequence. It'll change in a very small way. And that's pretty much it for introducing metallicity. We'll get into the details of this later. In particular, we'll get into the idea of where you form the different types of elements. So iron and oxygen form in different places, or can form in different places, and what that means then for metallicity and how it will affect the evolution of stars as we go back in time.